Good afternoon, everyone. I hope that you had a fantastic weekend and that everybody's doing okay today. Today we're looking at the next lesson, which is 30.10. This is dealing with solving exponential equations, and this lesson can be found on page 8 of your current lesson handout. An exponential equation is an equation basically that has an unknown in the exponent. So as an example, 2 raised to the power of x is called an exponential equation. The variable is in the exponent. And to solve these equations today, we are looking at using a common base. If a common base is not possible, and I will give you an example of that when the time comes, if a common base is not possible, then you're going to have to use something called logarithms to solve the equation. So the first equation says 7 raised to the 4x minus 5 is equal to 7 raised to the 2x plus 3. Now let's stop and think about this. How is it possible that 7 raised to the 4x minus 5 and 7 raised to the 2x plus 3 can be equal to each other? Well, they both have a base of 7, so the only way they're going to be equal to each other is if their exponents are equal. Which means that 4x minus 5 has to equal to 2x plus 3. And there are usually a couple of different groups of people when I explain this to them. There's a group of people who go, well, that's obvious. If the bases are the same, the exponents must be the same. But then there's another group of people who are maybe a little bit apprehensive about what's going on here. It isn't that we're canceling 7. We're just saying the only way these two things can be identical to each other is if the exponents are identical because the bases are identical. So you may have to give that a little bit of thought. If the bases are the same, the exponents must be the same. This is a grade 7 equation to solve. There is no question about how to solve this. You're going to add and subtract terms from both sides until you get the x's on one side, the numbers on the other. If I subtract 2x from both sides, I get 2x. If I add 5 to both sides, I get 8, which means that x is equal to 8 divided by 2, which is 4. Again, the algebra involved in solving this is very, very elementary. So the answer is x equals 4. Just to drive this home, and we're certainly not going to check all of our answers today, if I were to do a check here, the left-hand side would be 7 raised to the 4 times 4 minus 5. The right-hand side would be 7 raised to the 2 times 4 plus 3. All I'm doing is putting my solution in for x on the left and the right side. And what I end up with on the left-hand side, 4 times 4 is 16, minus 5 is 11. So I get 7 raised to the 11. When I look at the right-hand side, I have 2 multiplied by 4, which is 8, plus 3 for an exponent, which is 11. So you get 7 raised to the 11. Example 2. Well, example 2, the bases are not the same. So now we have to make the bases the same. And it turns out that 81 can be written as a power of 3. 3 raised to the 1 is 3. 3 raised to the 2 is 3 times 3, which is 9. Three raised to the 3 would be multiplied by 3 again, which would be 27. And if I take 3 raised to the 4, that's 3 times 3 times 3 times 3, that's 81. Which means that 81 in our equation can be rewritten as 3 to the 4. And now we have a common base. The base on both sides is 3, and that means the exponents must be equal to each other. I subtract 1 from both sides and get 3x equals 3, which means x is equal to 1 when we divide both sides by 3. That's the solution. 36 raised to the 2 minus 3x is equal to 216 raised to the x. Now in the last question, we were able to take the smaller base of 3 and raise it to an exponent to get the bigger base. So let's see if that works with 36. Maybe 36 squared gives us 216. And if 36 squared gives us 216, then we can use 36 as a common base. I think most of you recognize that 36 squared is not going to give you 216. It gives you, turns out to be 1296. And all that is telling us is that 36 is not the common base. So what is the common base? Well, let's go to the smaller base first and ask ourselves if it's possible to write that smaller base of 36 as a power. And the answer is yes, it's 6 squared. So 36 is 6 squared, and that is raised to the 2 minus 3x. Well, that must mean, if I'm asking you to solve this by using a common base, it has to mean that 216 can be expressed as a power of 6. So we're going to try a power of 6 now. 6 to the 1 is 6, 6 to the 2 is 36, 6 to the 3, and if you check it out on your calculator, 6 raised to the 3 is in fact 216, which means we can write the right-hand side as 6 cubed raised to the x. And now we have to go back and review something from an earlier math level. You learn this in both grade 9 and you review it again in grade 10 when you talk about exponent laws. If you have a base raised to a power and that whole thing is raised to a power, we call that a power of a power. And if I had r raised to the a, then raised to the b, it's equal to r raised to the product of the two exponents. When you have a power of a power, you multiply the exponents. The left-hand side becomes 6 raised to the 2 multiplied by 2 minus 3x. The right-hand side becomes 6 raised to the 3 multiplied by x. So I'm multiplying the two exponents in each case. Now that the bases are the same, the exponents must be the same, which means that 2 multiplied by 2 minus 3x has to equal 3x. Not quite a grade 7 or 8 equation, maybe a grade 9 equation. We are going to have to multiply that 2 into the binomial first to get 4 minus 6x equals 3x. Now we can solve that equation. If I add 6x to both sides, I get 4 equals 9x. Then I divide both sides by 9. I get x equals 4 ninths. So 4 ninths is the solution. The next example has 5 raised to the x equals 625 root 5. Given that on the left-hand side I have 5 raised to the x, and 5 is a prime number, there's no other way to write 5. That's telling me that the common base must be 5. So what we need to figure out now, and you have the aid of a calculator, is what 625 is in base 5 and what root 5 is in base 5. Well, you should know root 5 is 5 to the half. And we can figure out with a calculator what 625 is. Is it 5 squared? Well, no. When you put 5 squared into your calculator, you get 25. 5 cubed is 125. But 5 raised to the 4 is 625. So we end up with 5 raised to the 4 multiplied by 5 raised to the half equals 5 raised to the x. Now, when you, this is going back to grade 9 and 10 again, when you have a base, I'll call it r, raised to an exponent, and you're multiplying by the same base raised to another exponent, you add the exponents. And note that the r is still the base. So over here, when we add these exponents, we're going to have 5 raised to the 4 plus 1/2. But it's still a base 5. I'm mentioning that because some people might be tempted to put the number 25 in there instead of 5, because they see 5 times 5. The base stays the same when you add the exponents. That means that x has to equal 4 plus 1/2. It would be nice to put this in fractional form, which is 9 over 2. You could express it as a decimal, which is 4.5, but the answer is 9 over 2. Now we're going to move away from that and just talk about how we can solve things graphically. Right now, it's impossible for you to solve this equation because 12 2/3 cannot be expressed with the same base. So what we could do instead, and this is something I guess you could always do unless you're asked to show your work, is we could solve this graphically. I'm going to put in for y1 12, and for y2 I'm going to put in 2 divided by 3 in brackets raised to bracket x divided by 4. Now we should have some general idea of what 2/3 raised to the x over 4 is. We have learned that if the base is 2/3, you are going to have a decreasing exponential function. So 2/3 raised to the x over 4 will look something like that. We also know that when you graph y equals 12, it's going to be a horizontal line. The reason why I drew that is it's going to give us an idea of where we have to look to find the point of intersection. We're going to have to look in the negative direction. Normally, what I would say to everybody is always try zoom standard first, but zoom standard, I mean, I can show it to you. If I go zoom 6, I'm not going to see the 12 because zoom standard goes from -10 to 10 in each direction. So I'm going to have to adjust my window settings to a higher y value if I want to see the 12. And there it is. And I can see that this graph of 2/3 raised to the x over 4 is going to intersect with 12 someplace to the left of where my window setting is. So I'm going to have to go to a more negative minimum x. I would just go -50. I'm suspecting that will be enough. If it isn't, I guess I can increase it again in the negative direction. But it is definitely enough. So now I can find the point of intersection by going to my calculate menu, choosing intersect, and hitting enter 3 times. The solution is approximately, in decimal form, -24.5. And 2b, solve this one graphically. So I'm going to put in 75 raised to the bracket 2x minus 3. And I'm going to say right now, I know that this is an increasing exponential function because the base is 75, but it's going to increase very, very rapidly. A factor of change of 75 is going to increase things dramatically. I'm going to show this to you by going to my table setup, starting at 0 and going up automatically by 1, and then looking at my table. And you can see that as soon as we hit x equals 4, look at the value of y when x is 4. It's 2.37 billion. So this really goes up quickly. Now I'm going to look at 2.5 multiplied by 3 raised to the x. I guess I could go to my table and start comparing things here. It's definitely the case that they're intersecting someplace in the low values of x, but I want to go up to quite a high value for y. I'm going to go zoom 6 first. So I can see that they are going to intersect quite a bit higher. I'm going to have to go to my window setting and go up to, I don't know, I'm going to go up to 150. If that doesn't do it, then I can go up further by changing it again. I can definitely see the point of intersection. When I use the calculate menu to get a solution, what I'm getting is approximately, it's really grinding away trying to find it. There it is, approximately 1.84. And again, these are decimal approximations for question 2. And that's it. Solving things graphically, everybody, is a very nice tool to have at your disposal, because if you are doing some work on a written assignment, you could always check it graphically to find out if the answer you're getting algebraically is right or not. But the main idea behind this lesson is that you want to convert both sides of an equation to a common base so that you can set the exponents equal to each other. Your assignment is on page 364, number 4 and 5. Don't forget a couple of things. Tomorrow is a Google Meet day, so if you have any questions from the applications of exponential functions from last week, we're dealing with compound interest, exponential growth, radioactive decay, or you have any questions from the work from today's lesson, then show up for the meet and I will help you out. The second thing to remember is assignment number 4 is due tomorrow. Hopefully you haven't left it and forgotten about it, but it's almost done or potentially even done. Have a great rest of the day, you guys. We'll talk to you soon.